My name is Marco Verdicchio. I work as a high-performance computing consultant for SURFsara. We are based in Amsterdam, in Science Park, a huge university campus that is in the center of Amsterdam. And our company is about 80 people, 50-50 between consultant and more system program and more technical people. I'm one of the consultants. And what we do in SURFsara is all related to high-performance computing. So our main daily work is to work with our systems. We have two HPC systems, Cartesius and Lisa, very similar to Mare Nostrum, the one you want to work today. Much smaller, but same approach. We also do user support, helping users that wants to run on our machine, installing software, helping with their own code, and etc. We do training like this I'm doing today. We work on a lot also development, so especially in computer science, HPC, and we are involved in European projects. You may have heard about PRAISE and other CompBioMed, the project that is organizing this training. Personally, I work heavily in CompBioMed. I'm one of the people of SURFsara working in CompBioMed. And what is CompBioMed? CompBioMed is a European project. Is a European user-driven center of excellence in computational biomedicine. The idea that the goal is to promote the uptake and usage of high-performance computing in biomedicine. And we have a users base that comes both from academia, industry, or clinical practice. So guys, there are three main areas of focus of biomedicine: CompBioMed, cardiovascular medicine, neuromusculoskeletal medicine, and molecular-based medicine. But the project is really open and to all biomedical science. And the main activity, especially in the HPC field, is to support and facilitate modeling and simulation in biomedicine, develop and sustain software tools. You will see later today the usage of some of the software used in biomedicine, high-performance computing software, and also, especially also enhance industry, healthcare sector, the usage of HPC. There are several partners, core partner and associate partner that works in the HPC field, SURFsara, IPCC, but also cloud provider that are associate partner of the project and work heavily with us. We have a lot of use cases, a lot of very good code and application that runs all over the world in the largest supercomputer in the world. And if you're interested in more of the science and more of the content of the project, please check the CompBioMed booth at the VPH conference. You will see a lot of more of example and explanation of what we do there. So what I'm gonna talk today is an introduction. My 2 hours is mainly focused introduction to HPC. So today we're gonna show you what is a supercomputer, what I mean when I say supercomputer, working with a supercomputer, how you access, how you use, and then some basic Linux and HPC commands. So getting started, basic command, bash scripting. If you already know these things, it's gonna be a refresh. You have the paper that I gave you. It's a list, it's a reference card for some of the most used Unix command. You can check there what the command does and what is the different command. And then at the end, I'm gonna show you briefly how to run jobs on a supercomputer, especially Mare Nostrum. I prepared for you some exercise example. I will give you a link, you will download. And then in the last 45 minutes, half an hour, we will have also hands-on and show you how to run these commands. So what is a supercomputer? Okay, so a supercomputer is actually a really large example of a lot of computers. These pictures are also very beautiful, especially Mare Nostrum. I don't know if you ever visited. It's a supercomputer in a chapel in Barcelona. And why we need to use a supercomputer? First of all, it's a multi-user system. You all log into the same computer and use all the same hardware. Mostly all, 99% of all supercomputers are Unix-based OS. And they run very optimized software to run parallel calculation and run very fast your simulation. It's composed, as I say, by many CPU. and that's the strength of the supercomputer. You combine the power of a lot of CPU and specialized hardware, like connection between the CPUs and accelerator that can be GPU or FPGAs. And that is also, this is very important, also has large storage. So both in the file system and also large memory for storing of data, or also efficient for very parallel I/O, so when you write and read a lot from files. These are all characteristics that define what a supercomputer. There are a lot of supercomputers in the world. This is a list of the top 5 in performance supercomputer in the world. You can go to the website www.top500.org to get the updated list of the top supercomputer in the world. How you measure the power of a supercomputer? There are like some specific specialized algorithm that people run all over the full system, and these algorithms produce some number that here are R peak and R max, and are the number of operations that a supercomputer can do in a second. I'm not going to the details of what a floating point operation is, but that's generally what sets the tag of a supercomputer. So now you know what it is, more or less. Why you use supercomputer? There are several reasons to use a supercomputer, but the main two is to scale up your code or scale out your code. This means, so scale up means when you have your code is running, for example, on your laptop, small machine, but you cannot run your simulation because it takes too long, needs too much memory, or for example, you need the GPU that you don't have installed on you don't have configured in your laptop. So this is called scale up. So you're taking your simulation to a larger, more powerful computer that has larger memory, faster CPU, and specialized hardware. But that's not the only reason. You can also scale out. For example, we will see what a parallel application is. And basically, it's an application that runs on use multiple cores simultaneously, and there's a lot of communication. You can run this application on your laptop, on few cores or on serial, but you want to run larger input file or a bigger model. So you need more CPU, more compute power, and that's you can scale out by using a supercomputer and porting your application over a large number of cores. I don't know if you've seen, but there are supercomputers with hundreds of thousands of CPU that you can run all over the system. And this means also you don't have to have a large simulation. You may want to do the same simulation over and over, for example, Monte Carlo, sampling, or this kind of simulation that you don't need to run only once, but you need to run thousands of times. Same things, you can go on a supercomputer and use the thousands of CPUs available to run your simulation. So how is really to work in a supercomputer? Unfortunately, it's not like this anymore. This was like long time ago, very vintage and cool picture. But it's actually not like this. Now what you do, what you look at when you work in a supercomputer is this. It's a terminal. Because the reason is that a supercomputer is a remote machine. You are not interfaced directly. You connect the user here, connect to a login node through the terminal, to SSH protocol is a protocol to connect between remote hosts. And then on the login node, where you can type your commands, you submit your jobs to the supercomputer. The supercomputer has a batch scheduler. It's a system, I will talk a little bit more about this later. It's a system that manages the compute node of the supercomputer. And you basically prepare your job as a mission script. We will go through this in the following of this class lesson. You prepare a script, and then you submit your script with a sort of recipe of all the steps you need to do in order to run your simulation. The batch scheduler then takes your script and take care of submitting your simulation to the compute node. And of course, these are interfaced with a shared file system. As I was telling you before, is optimized, fast I/O, and very large file system that are specifically designed for high-performance simulations. So basically, these are the elements that you need to know when you use a supercomputer. The login node, as I say, is the interface between the user and the supercomputer. Is a node, a specific node where you can edit and transfer in file, compile program, and prepare your simulation. You're not supposed to run your simulation on the login node. You cannot. What you can run your simulation on the compute node that, as I told you, you cannot access directly, but you interface with them through the batch scheduler. That is, the system is a software installed on all over the supercomputer, then manage your allocation, the queuing of the job, and accounting of your login, your account, and the logins of your coworkers, for example. And the last, but not the least, as important, file system. We usually have parallel file system with efficient I/O for reading and writing files. And also nodes, they have usually local disk attached that are for faster, even faster I/O when you run your simulation. So basically, when you work, the real work when you interface with a supercomputer is, we can divide in 3 phases. So you first log in to this remote machine through through SSH, and you transfer any file, input file that you may need with other command SCP. You will do this through command line. There are some supercomputers that offer a graphic user interface, but today we're gonna go only through command line options. Once you're logged in and you have all your files there, you will prepare your jobs, your simulation, input file, the job submission script, that is that recipe that I was mentioning before, where you explain step by step the steps needed for your simulation. You load or you install all the software needed, and then basically you submit your job. And so you send your job to the batch scheduler that will take care of queuing, putting your job in the queue. When the compute node are free, it will allocate the compute node for you and run your job on the compute node. You can submit, monitor the status of your job, and at the end, when the simulation is done, you can retrieve your output to the local machine or do some remote visualization directly on the system. We will see also these a little bit in details later. So let's start now. First part, as I told you, is more focused on how you log in to the HPC system. I will show you all the steps, and we will go through also some hands-on. So in the meantime, when I talk, you can try the commands. Everything should work. So you can already try to SSH and SCP. Okay, to start, we wrote this also in the message that you received before the course. You need to install some tools on your laptop if you want to work with Mare Nostrum. If you are a Linux user, you are done already, well equipped. If you are a Mac user, the terminal is pre-installed, so you should be fine for 90% of the things we're gonna do today. But if you want to do some remote visualization, so visualize something on the supercomputer, you need to install Xquartz. It's a X server for remote visualization. It's a small tool that you will install and never touch. Then when you will run the command to start the remote visualization, it will start up and give you the window. If you are on Windows, you need to install additional tools. There is a PuTTY, is a terminal emulator, very basic. I suggest you to install MOBA Xterm. It's a more developed tool. It has a more graphical interface, nicer, easier to understand, and it includes a lot of other tools like the X server, the SCP tool to transfer files. So if you haven't yet, please install one of these two tools on your local machine. Otherwise, you will not be able to log in to Mare Nostrum. So the reason, as I said, is to get what is called terminal, and because all the commands we're going to run, all the interaction we're going to have with the supercomputer will be through the command line. So this is a terminal, an example of a terminal on Mac, and this is the command line. Basically, here, this is a terminal local to my laptop, so it's not remote. And these, I can type commands there and get the command executed. So call my application, open a file, copy a file. We will see a lot of this. Once you have the terminal, what we're going to do is connect remotely to the Mare Nostrum supercomputer. And for this, we're going to use SSH. That is an acronym for Secure Shell. This is a protocol to establish like a secure connection between your local computer and Mare Nostrum. This protocol permit to authenticate yourself, so you will have, as I say, a username and password that are assigned to you. The system knows your username. Through SSH, you exchange information and confirm that it's you. And then through SSH, you can pass command back and through. So you type on your keyboard, the command through SSH go to the remote host and run there. So to log in to Mare Nostrum, you will have to, this is an example. So this is the command line. You type SSH and white space, and then your login at mn1.bsc.es. You press enter, and you will get this line asking for password. You will type your password. Don't worry if nothing appears. It's like this. You don't see the character you're typing when the password is typing, but you're actually typing. When you're done, you press enter, and you should be logged in. Again, this is hello, hi. This is again your username, and this is the Mare Nostrum login node, the host name. That's also here. So your username and the Mare Nostrum host name. If you have any question, please stop me and ask. I will be happy to answer. So after successful login, this is what you get. You will get some message of the day, nicer print of hello, welcome to Mare Nostrum, and things to welcome on your machine. But the important thing is that you get this, the command line. And this shows you that you're actually logged in to a remote host, because this is your username at login1 is the name of the login node you are connected to. It may be different in your case. There are multiple login nodes, so you may get login 2 instead of login 1. This is only an example. And now that you are here, the system is ready to accept commands from you. So any command you type, it corresponds to an action that the system executes. Okay, so let's start to see some of these commands. As I told you, the supercomputers, the operating system is Linux. So before running real jobs, I'm going through a brief introduction of some Linux command that we will use it. In the paper that I gave you, it's a much more extensive list of commands with explanation of what each command does. So keep it in front of you, and if you have any question, again, please ask. So first things, why we use Unix and why supercomputer Unix? Well, Unix is an operating system that basically controls the other part of the computer, allocates resources, and allows the user to access the system. The real advantage of Unix are that is multi-user and multitasking. So you can have multiple users, and each user can have multiple tasks running. It's designed to be machine independent, so you will see Linux installed on a different type of hardware. And it's a very good OS for software development. You will see a lot of the tools you need to compile your code, to edit file, to parse information are all available native on Linux. And is suitable for scientific application. A lot of scientific applications are designed on Linux for Linux. So that's the main OS we're gonna manage today. As I say, this is the screen you got when you logged in. I don't know if you tried already, but this is the welcome message, it's called, of Mare Nostrum. It's not really visible, but there is BSc logo, some explanation. Here, the user guide. Please read the user guide. When you don't know how to interface with a supercomputer, every HPC center, we prepare user guide for users. So if you don't know commands, if you don't know how many nodes I can ask in Mare Nostrum, the user guide should answer all these questions. And as I told you, you are logged in. Here is the command line, as I showed you before. And now you can actually start running Unix commands on Mare Nostrum. What is a Unix command structure? The Unix command is a command that you type on the command line, and in the back end, this corresponds to an action that the OS, the computer, start doing. Can be any type of operation, we will see, and in the example, there are more sophisticated commands that I will describe. But basically, a command in Linux is first the command, the Unix shell or the interface you have with the OS is taking this command and trying to find a program called mkdir. In this case, is simply to make a directory, to create a new directory. You can pass to the command options. Usually are, the options are correspond, it's usually a dash and a letter or multiple letter. Every command has its own options, and we will see. They are optional, so both options and argument are optional. You have to put a command if you want to run something. And then the command can take arguments. So for example, in this case, as mkdir is the command to make a new directory, -p is an option to make not only to create also parents directory of the directory you are creating. And this command takes at least one argument. That is the name of the directory you want to create. We will see more in details other Unix commands. You can check on your command reference paper. The important thing is that commands in Unix are case sensitive. So mkdir is lowercase. If you type mkdir uppercase, will tell you command not found, because mkdir uppercase is a different executable for the OS. So are case sensitive, everything, both options and argument, and every part, so command, option, and all the other arguments you want to pass to the command are usually separated by space. Sorry. So a typical Linux Unix command is like this: the command, option, argument 1, argument 2 if you need more than one. You can also pipe multiple options, so flags, -p, -r, blah, etc., etc. So, and this is for every Unix command that you may find. So, where to find some help? There are a lot of options. How you know how many arguments a command takes, how you know which option do what. Unix provides itself a way for user to know more information about the command. You can use the flag, that's an option, --help. This is one of the options that is common to every Unix command usually. This is, for example, another command. If you type this, you will get a description of what uname does and the syntax. So if you can, which option it takes and how many arguments it takes. You can also see the manual of this command. It's a more extensive set of information by typing man, M-A-N, and then the command. This works for every command in Unix. So you type man mkdir. It will show you what mkdir does, how you use it. Or you can also use the info command, similar to man and help, give you other set of information. What you will get when you type, for example, man of a command, this is uname, is this. So this is the name, uname, and it tells you what it does. It prints system information. This is the syntax, so it's uname and options. Doesn't get any argument, doesn't need any argument. You can see here only options. And then there is a description of all the different options. So you see help, display, this help, and exit. There are all the different options. You can run these for every Unix command that you have, and you will see that all the different information. So let's try type some command. This is some example. You will get, this is the command line. After you type a command and press enter, you will get the output of the command in the second line, and then back the command line. So for example, this is some example quickly I'm going through to show you what you can do, basic operations. So you can ask where you are in the file system, which folder, which you, under the tree of the folder by typing pwd, and present work directory is the acronym. And you will get this, that is the location of where you are now. So basically now you are in the folder home. Inside home there is a folder nct00, and inside nct00 there is this other folder that is the folder of, that is the name of the username. You can then see which files are there with ls. ls is list, and you get the list of files that are present in that directory, for example. You can pass additional options, as I showed you before, like -l, -l. This is a stand for long format, and it gives you more information of it. These are the three same files here. This is only the list. This is the list plus the time created, the permission, the user who created, etc., etc. Type man ls to see what ls command does and what the option, what they do. You can also not only ask where you are or what file are there, you can move around, cd, again, change directory. Every command usually tells you, or it's an acronym or a short version of what actually does. So cd stands for change directory. You can change to the directory subdir. This is the tilde sign. It's a sort of abbreviation for the path to your home. We'll see later. You can do cd ... means up. It goes one directory up. You can do cd without arguments. You will see in the man of cd. If you type cd without arguments, you immediately get moved to your home directory. That is your main directory in Unix. And you can do a lot of other operation with directory. Create a directory, remove a directory recursively, so with all the files inside. Be careful when you run this command, for example, because this you don't get in Windows. Are you sure you want to delete your files? It deletes your files, and don't ask. Unless you specify an option. There is an interactive option, -i, that will ask for every file you're going to delete if you want to delete. But the default behavior of Unix is that automatically the OS really trusts you. So it trusts that you know what you're doing. Another things to know, this is not related to command, but is in general of OS, of Unix operating system. You have a relative path that means that is the path from your current position. So imagine you move UCD into a directory, and so you are in this directory that contains another directory that is called dir, and this is relative path. So you are already in your home, and you have in your home a directory that is called dir. If you are somewhere else, you can still refer to that directory, but starting from the root of the operating system. So Unix is a tree operating system. The file system is sort of tree, so you have a main point, the root, and then all the other folder and subfolder follows. So if you want to point to the file here, mydata.out, you can do the relative path from your current location or the absolute path from the beginning of the tree. Again, this is show you see, /home, NCT folder, NCT0004, and then the dir directory where my data out is. This is important when you move around or where you want to ls a different folder. You can do both. One does not exclude the other. You can start from your relative path where you are, or you can describe or point to the file from the root of the OS. You can do operation on files. So for example, is CP files, copy to directory, moving files, or having like, this is important, we will see later, how to copy a file to a remote host. So these commands are local on the remote machine. So basically here you're copying file 1 to make a copy of file1.txt called file1.copy. You can copy a file into a directory locally in the system, or you can move a file into another directory and rename it as a file.txt.new. These are all examples. Again, you can type man of these commands, look on the paper that I gave you, or the command and -- help to know what it does. This is similar syntax to CP. So you see you have a file, original file, and a destination file. But this SCP stands for secure copy. And this is an extension of SSH to copy file remotely from your local machine to remote host. So the addition that you have to put respect to the normal CP is the host name of the remote system you want to copy the file to, and your login name, because this is again based on SSH. So SSH was checking your identity through username and password and confirming that was you and giving you access to the folders assigned to you on the remote system. The same apply to SCP. So here you are copying a file locally to Mare Nostrum in this location. Here you're doing the opposite. You're copying a file from Mare Nostrum at this position to here. Here to the present directory in Unix, you can do it with the dot. So one dot means present directory, where I am now. So if you want to copy any file from everywhere to where you are now, you put the dot as a final destination. And this is how you copy recursively a directory to Mare Nostrum. If you don't put after the column, so the syntax of SCP, and again, I suggest you to check the syntax every time of every command with the man or help options. How SCP works, you have to put the host name, username at host name, and then column, and then the path where you want to copy the file on the remote machine. If you don't put anything, he takes the home as a final destination. So if you're okay in copying everything into your home, this is the way to go. So as I told you, I prepared for you some examples that I will ask you to download from this website. So bit.ly HPC_CBM. You will, it's a GitHub page. On the top right, you have a clone or download button. You can download the zip file, and you can download locally. Basically, you will have a file called intro HPC_CBM-master.zip. This is a zip file that contains all the examples we're gonna go through today, even more probably. And what you have to do is to copy this zip file with the SCP command, as I showed you right now, to Mare Nostrum. So once you downloaded the zip, you do scp, the name of the zip file, and then your username at host name, and then put simply colon, then it will end up in your home. Once you've done this, and now it's simply to show you what is needed to be done. We can go through this later. You can log into Mare Nostrum and extract your zip file there, so using the unzip command to the file. These were some of the examples of the Unix command you can run. There are really a lot of them, and there are commands for file editing, view, touchless, cut, head, tail. Everybody has his own different behavior. System tools to history of the commands you typed, to compress and zip files, as you've seen. So I really suggest you to look at the paper I gave you, and also online, if you type a list of Unix command, you will see extensive list of everything. So, but what if you want to run multiple commands? Like, of course, when you're really now that we're gonna train or try a few commands, or if you want to simply copy file, it's easy, you can do interactively. But what if when you have to run your simulation, and you have to do a lot of commands, one after the other, copy file, and on top of this, I told you that actually you're not interacting directly with the compute node of the system, but you have to prepare a recipe with all the commands you want to run, and send it to the batch system. So what to do when you need this, or maybe you want to design a workflow? Well, in that case, there is something in Unix called scripting that is very useful. Basically, a bash script, bash is the shell, the main interface, the default interface you have with the OS. All the commands I'm going to show you today are based on bash, but there are other shell that you can use if you are more expert user. And they work the same, simply the commands are slightly different. So with bash and with Unix, you can create what are called scripts. So a script is a plain text, it's a text file that contains on each line all the commands you want to run. Any command that you can run on the command line, you can put it inside the script. Actually, a script has something more. They can use some special variables that the command line they don't know. But basically, the script is a text. It's a text file with all the. It's a text file with all the commands you want to run in a workflow or in row. And then you can execute the script. So why? What does it mean you can execute the script? Basically, in Unix, the difference between a program and a text file is what is called file permission. So each file you can give to users and of the system different permission. You can let everybody to read and write the file, or you can allow only yourself to read and write the file. And you can also allow yourself or other user to execute the file. When you give to a file execute permission, so that allows other people to run it, basically the operating system gets all the commands that are in the file as a bash command, as a Unix command, and it's try to execute one after the other. As I told you, a command is a call to a program that is an executable. So basically, giving a permission to execute to a file, that case is simple.sh, will give you we basically allow the OS to get every line in the file and execute them as a command that called the executable behind. I prepared for you some bash scripts that are in the folder that you should download from the website. This is how a bash script looks like. So in the first line, this is a line that always is there if you want to run a bash script as an executable that tells you simply that this is based on bash. As I told you, you don't need to know other shell today at this point, but there are other shells if you know other commands or have other options. Simply, this tells that all the command that follows will be bash commands. And then here is what I was telling you. Every line is a different command, and when I run this script, you will see that the OS executes one after the other all commands. We will look at the script more in details, but basically here, I don't know if you can see it in red on black, but basically these first two lines and last two lines are simply print of some type of screen. These are the commands that actually will do the work. And as you can see, as I was showing you before, this is the command and this is the option. And this basically tells the redirection, the arrow tells to put any output of that command into a file. Yeah, okay, that's another important thing. That's the thing I wanted to tell you, that bash scripts, as well as command in Unix, they have a stream of input-output that usually you give something in input, a command, and the command prints something in output. Not always, but most of the time. And these are named, and if any errors occurs during the execution of the command, it will print you also an error message. These are all different streams and are called basically standard input, what you give in input to the command, standard output, what is the output back, and the standard error is the error file, the error that is generated. We will see in the example that you can redirect and then you can create all the workflow and stream of input output in a Unix command. This is one of example. I don't want to go really deeply in this. We have two example scripts, but this is a little bit to show you the potentiality of this Unix and all the commands that you have. So it's not simply a set of commands to copy file and create directory as I show you, but you can pipe multiple codes together, process the output of one as the standard input of the second command, etc., etc. Here it's the second script that you can find in the example under the Unix folder, and this is much more complicated. You see, you can put comments to ignore everything. This is another special variable that I was telling you. If we have time, we will go through this script, and I will show you what every command does to show you a real example. You cannot hear in this script, this is the second part of the script. It's a long file. Other things, it compiles a code, the C code to an executable, and then it runs, and then put the output in a file, the error in another. So it's really powerful language that you can do a lot of things with it. Yeah, this is how you execute. And so now we know how to, I give you like the first instruction, how to prepare a job, how you interface with OS, but now you need actually to run the jobs in the queue, on the system. And that, if you remember from the first part, this is done through the batch scheduler. Basically, all supercomputer use a tool to manage the compute node, so the node that they really do the calculation. As I told you, you log to the login node, and then you are not directly interfaced with the compute node. What you do is submit a job. You prepare a job script using bash scripting commands and Unix command that I show you. And you submit a job to a tool that is called the scheduler, the batch scheduler. This tool, basically, what it does, it manages all the compute nodes. So it manages for you. It allows to run many jobs at the same time. You don't have to understand which nodes are free and ask specifically the nodes. You submit, you forget about your job, and the batch scheduler will automatically assign to you a different part of the machine. This is very important for HPC system because are a multi-user system. So you submit your job, but at the same time there are other tens, hundreds of people that are using the system, and they are maybe submitting at the same time. So how will work if it's interactively is impossible because you will have overlap of multiple people running on the same node. The batch system takes care of this. As I told you, you send the job to this tool. This tool will check how many users are running, how many resources are free, put you in a queue of users that can run on the compute node. And when it's the time, it will start, allocate the resources, and start your job. When the job is finished, the batch system will close, free the resources you are using, and give you back the output that your simulation is producing. This is also important for what is called system load balance, in the sense that the batch system also allow to have all the compute nodes almost equally occupied. So there is no really imbalance of system, like a user monopolize all the system for himself, or only part of the hardware is used. The batch system will put down in the queue users that are heavily using the system and promote other users to share the resources as equally as possible. Of course, it's not always possible, but this is a big work for the batch scheduler, and this is one of the main reasons why we need the batch system. So, how you interact with the batch system? There are specific commands, and in this case, Mare Nostrum is in Mare Nostrum the batch system is told is a Slurm. So there are Slurm specific commands, and basically you prepare your job script, as I showed you before. You have all the commands you want to run in your simulation, plus some other option that I will talk about later. And basically, you submit your job script to the system, so using the batch command as batch and the name of your script. You can check the job you submitted with the SQ command. You type SQ, and then it will give you the list of all the job and the status of the job, if it's actually running or if it's actually in the list, in the queue. You can also, you did an error and you don't want anymore to run your job, but this is already in the queue waiting for resources. You can cancel with scancel. And you can actually also run a single command through the batch scheduler with the srun command. But this is actually a command that is used more in the job script to execute parallel run. But this is something more expert. The main commands you need to submit a job, check the job, and retrieve are these three: batch, SQ, and scancel. As I told you, the job script, the job that describes your workflow, the work you want to do, when you submit it to a batch scheduler, needs a little bit more of information, because on top of the commands you want to run, you need to specify the resources you need for that commands. So imagine you have your parallel simulation code you want to run. Okay, you prepare your bash script with all the commands, create the input, prepare the folder, run the executable, get back, do any part. But then you have also to specify, I want to run these on 10 nodes, 100 CPUs, I need this time, this amount of memory, and I want to run for 2 days. Because one important thing is to have both the load balance and the right queuing system. The batch scheduler needs to know in advance from you for how long you want that resources for. So you have to have knowledge of what you're doing. You cannot run a simulation and you don't know whenever it's going to finish, because you actually have to specify. Of course, if your simulation ends before the time you specify, the resources are freed and give to other user, and you're not paying or managing the resources anymore. But if you don't actually know how long your simulation will run for, and you ask for a shorter time, for example, you ask only for 1 hour and your simulation ran actually for 5 hours, then the queue system will kill your process, because you're not allowed to run more than the time you requested when you submit the job. So it will kill your job, and you won't have the final results of your simulation. So take care of the it's called wall clock time, so the time it runs the simulation. All this information, and many more you can give, are are passed to the batch system by simply putting at the beginning of your submission script, before the list of commands, some directives of this type. So it's the hashtag is batch, and then -- nodes. For example, this is one of the options, and then the number of nodes. There are many options. You can ask the number of process, the time, the quality. We will see some in the example. But if you want to have an exhaustive list of all these commands, please Google slurm batch or go to this website, and you will see the many options you can pass to batch. It's a very sophisticated system. You can pipe multiple jobs. You can have a lot of interesting things. It's important also to look at the guide, the user guide of the HPC system you're running, because sometimes some of these commands are sort of specific for a system. So every system has its own configuration of the slurm of the batch scheduler. So please take care also the user guide of the system you're running in, because they may have a different configuration. And this happened, for example, between Cartesius, the machine we have in SURFsara in Amsterdam, and Mare Nostrum. They are both configured with Slurm. So the batch scheduler is Slurm on both the machine, but we have a different configuration. We have what is called partitions. They use quality of services. It's slightly different. Please check the user info. Another quick thing to go through, how you get your, so now you know how to do basic Unix command, submit a job to the batch system. But how you run software. So there are like much more professional or expert software than simply bash commands. And a lot of this software are already installed and optimized for the system by the sysadmin of the system, people that work in HPC Center. And this software already pre-installed on the system are made available to the user through another tool that is called modules environment. So basically, when you log into a system, you can always type module avail to get a list of all the software installed by the HPC people that works on the system already on the system. You can have multiple versions of the same code. So this is Python, for example. I don't know if you know Python software. If you tap module avail, you will have a list of all the software installed on the system. If you type module avail Python, you will have the list of all the different Python installation that you have on the system. Then you want to load the specific version. So you need Python 2, not Python 3, you know, the difference between Python 2 and 3. You can load the module Python with a specific version. And anytime you're gonna use the command Python after you load the module, you will get Python 2. If instead of Python 2, 7, 13 in this case, you would have loaded Python 3, the command Python will be associated to the Python 3 executable. You don't have to take care of these things. It's the module environment that does for you. So you ask which software you want to load, which software you're going to use. You load it like this, and then the system is set up for you to use that software. This is, for example, a list of all the software installed in Mare Nostrum, some of them. And I don't know if you can see, but if you type module avail on the system, you will have all the information. And basically, yeah, that's it. Last thing is important to know, and again, if you remember initially the slide I was showing the component of the supercomputer, I repeated multiple times that an important thing is the file system, the real hard disk and hard drive. You're running your file, you create files. This is very important because a lot of scientific applications usually have to do with the large files or a large number of files, and these things can be it's important to know the file system of the machine you're running and to use the right disk and memory for different operations. So this is also very important, and this is one of the reasons why I told you look at the user guide of the system you're running on every time. Every system is configured slightly different, and the usage of a right file system, right disk, can affect drastically your simulation. So every time check with the user info which file system are set up for parallel I/O, for example, or which system are set up for long-term storage of files, and there are all these. For example, in Mare Nostrum, this is an example. Every system is configured differently. There is a root file system, that is where the file system is installed and where you have your all the operative system files. You are not allowed to access this part, for example. But then there is a GPS file system that is like a parallel file system distributed. That is where all the home directories and all the directories where you actually write and read files are. So it's important to know that you are here, for example. But then, and this is when I'm telling you, the knowledge of file system, it can affect drastically your simulation, is because, for example, in Mare Nostrum, you have the local hard drive plugged directly on the compute node where you're running your simulation. So if you're, for example, you are producing a lot of files or very large files, but you're not writing these files to the local hard drive, but you're writing them in your home directory, yeah? This will slow down a lot your simulation, because not only the file needs to be computed, but then it needs to be copied back to the home that is not local to the node, for example. If you know about these local hard drives and you tell your code to write all the file during the simulation, this local hard drive that is much faster accessed, and actually these are, I think, SSD drives, very fast and optimized for the computation, you can have, during your simulation, all the files written on the local hard drive, and at the end, in a single command, copy only all the files that you need, or all the files back to your home, where you can edit, where you can copy back to. This is something that is best practice when you use a HPC system. It doesn't mean that you cannot run if you don't use the local hard drive. It's simply that it's much slower and then not efficient. Okay, yeah, this is two examples. I'm not going through, explain you a lot of these things. These are the two examples that you find in the files that you downloaded from the GitHub. This is a simple script. One thing you have to know this is a serial script. I'm asking only for one core, one task. This other one is asking for 2 nodes. They are very similar. Actually are the same, and you will see if you run this in the hands-on later, you will see the difference for of the two. What produced the output? Yeah. So this is like how you do it. So you get this script. You do a batch of the scripts file. So batch is learn2.sub, and then you can check the status of the job that you submitted with SQ. And this is something like the output that tell you the ID of the job. The ID is an identification number to distinguish your job between the job of other users and yourself. Where it's run, the name of the job. Here, if you see, here I gave a name to this job. It's called test multinode, and here it's cutted, but it's the name of the job. If you submit multiple jobs, you can submit as many as you want, and you have the user who is running. The status, in this case, is PD, that means pending, so the job is still in the queue, waiting for resources. And this is the time when it starts running. This status will change to R, running, and you get the time that it runs, the number of nodes. And this is why the reason why you are in this status. So here none means that basically you are simply waiting for resources. So, okay, I think we have another half an hour and then the end zone. I would like to finish running through this small introduction to parallel jobs before starting the end zone. So basically, so far, what I told you so far are the basic to log into an HPC system, manage files, and run your own job. But all the things I told you, all the example I show you are simple example. The most advanced script that simply calculate a factorial number that's not like exciting. When you really need to use an HPC system is especially when you have parallel executable. So today you will see a lot of usage of parallel code later, especially, and but that's the main reason to use an HPC system. And I don't know if you're familiar with the idea of parallel versus serial job, but I try to explain you very briefly. I'm not going into the details of parallelism, etc. I simply want to give you the idea of why you need to use so many CPUs or such a powerful compute system. So basically, if you have a problem, you can break this problem in a series of discrete instructions, as I told you, like for example, the best script that I was telling you, or even like more mathematical heavy functions or procedure. You can always decompose these in a series of instructions, okay? When you execute these instructions serially, means that you're passing one instruction after the other to the processor. And before passing the following instruction, you need that the processor ends what work it was doing. So imagine like calculating, like for example, a very basic trivial example, calculating the paycheck of a company. Imagine a company has 100 employees and you have a software that you give the ID of the employees and it calculates what is his paycheck at the end of the month, okay? Basically you can break this problem in small instruction, one employee per time, and you have one processor that calculates. You pass the ID of the first employee, it does its math and give you the output. At that point, you can give the ID of the second employee, and so on and so on. These will last until all the employees are computed, all the paycheck are calculated. But what if I have many processors, like in an HPC system? Again, this is the same problem. You divide the same problem of paycheck of your 100 employees, but instead of giving all the 100, one after the other, to the same processor, you distribute, you parallel, you make it parallel, you use simultaneously multiple resources, you parallelize your problem, and you basically give, since every task, and this is important for this kind of parallelism, does not depend, since every paycheck does not depend on the other employee, you can give each ID to a different processor, and they all start at the same time. So if your company is composed by 100 employees, for example, and you have 100 processors, you can give to each processor one ID, and without waiting that the first one is finished to pass the second one, because all are independent. So you can go on like this, and basically, if you do some simple math and you try to, the serial code will take the time it needs to calculate one paycheck times the number of people you have in your company, because you're doing one after the other. If you have multiple processors that can split the job, and ideally you have one processor per employee, you can calculate the full paycheck of your company with the time you do one operation, okay? Because every processor starts at the same time. None of them is busy with calculating paycheck. They can start all at the same time and give you back all the output at the same time. Is it clear, this? Because that's something intrinsic in how you use like HPC. That's the one of the reasons. I also prepared like another example for you. In the parallel folder from the zip you downloaded, there is this Python parallel script, and there is another parallel Python serial script. Both the script, they do the same computation. So basically, there is a Python code that calculates the distance of 2 points of between all the distance or the pairwise distance of 2,000 randomly generated points in the space. And it gives you the shortest one. And it does this for 10 times. So it's stochastic things. Randomly position points in the space, calculate all the distances between each other, and find the shortest one. And you want to, for 2,000 points, and you want to do this 10 times to have some sort of average, or that's an example, okay? You will see in the script is quite complicated, but there is a way in which it calculates the time of execution of this part, so the computational heavy part. And you will see that if you submit the serial and the parallel is the same, I can assure you, it's the same load of work, you will see the difference in distributing parallel the job or having it done in serial one after the other. The script does multiple things that are useful also as a to see how a real script is. So it loads the appropriate modules here, and the way how it parallelizes the work to be done is basically exploiting a function of Unix that you can put a process in the back and give another process that will be executed on a different core. And this is done simply putting an ampersand at the end of the command. So basically, quickly, the difference, if you don't put ampersand, this is a do loop that submits this command 10 times, this command 10 times. If you don't put the ampersand, when you execute this command, this will stay appended and wait for the command to finish to get the second input, okay? And it does this for 10 times. If you put the ampersand, basically you are coming back. This is the loop without ampersand, so you pass one task to execute. The processor executes, remain appended. When it's done, give you the output and you get the second input. Putting the ampersand at the end of one command, you basically put the command in the background. So you let the processor compute, but it gives you back the command line to execute another command that automatically will go to a different CPU if available. If not, we'll come back to the first one, but it's not the case in a HPC system. And you will have this work done distributed in 10 different processors that will run at the same time one single calculation. In the parallel script, you will have also weight, different command compared to the serial one. And the weight is actually to, since you're putting command in the background, you want to wait at the end that all the commands finish. And so you put a wait to wait that everybody finished, because it's also not the same time. Sometimes it's faster, and the single computation can be slightly different for the load. But these are the main two differences. The ampersand at the end of the command and the wait at the end are the two differences between running in serial, one command after the other, or running concurrently in parallel. And that's why it's not a lot in the computing complexity of this type of job, is more on the logic. That's why I was telling you the difference between a serial execution and a parallel. This is the simplest way of parallelized an application. That's not always possible, because in this case, for example, we need that every task is independent from the other. But there are a lot of different ways of you can parallelize your code, and there are a lot of different computing languages, programming languages, or that you can use to make your code parallel. This itself can be the subject of a week of training in class. So I'm not going into the details of all this parallelism, but I'm gonna simply tell you that exists, so you know, and then some information about it. So the type of parallelism we just saw with the Python script is basically task parallelism. So you have many independent runs. You need simply to orchestrate this, so send in the background and wait for everybody. But it's all independent. If you run one or if you run 100 of them, they are all independent, don't need to know the results of each other. This is, for example, like Monte Carlo simulation of this type. You have Monte Carlo sampling, every point is different, and then you have at the end average or integration of the results, or parameter sweep. There are other type of more sophisticated parallelism. For example, if you want to do data parallelism, so you have, for example, a matrix, and you are working, the matrix is stored on some memory. You want to have multiple workers working on the matrix, but they need to talk to each other. So you have, you have shared memory parallelism. So basically, in one node, you have a multiple process that read and write to the same part of memory. This is memory parallelism shared. It's usually often implicit in the code. You don't have to explicitly tell the code to do that, but that's a very easy way to parallelize also your code. You can also, when you have multiple nodes, you have also distributed memory. Every node has its own memory. So on top of managing the parallelism, you have also to manage the data location, and that's very important. Yeah, this is like, for example, this is something, okay, so basically this is a schema of shared memory. So you have a single memory address that is accessed by multiple CPU. This is like a distributed memory where you have each node, each CPU has its own memory to access. And this is called distributed memory topology. But you can have also hybrid things in between. So you have a set of nodes, and each node is, the memory is shared between the compute element on the node, or GPU, CPU in this case. But then you have many of them. They are working all together. This is usually done through MPI and like partial derivative equation or time stepping. It's this kind of problem. And yeah, the important things to know, and the message I want you to keep from this, is that there are like specific computing languages and directives that you can use, like MPI or OpenMP, that are meant for managing this kind of different type of parallelism. So MPI is used to manage communication between different nodes. OpenMP is meant to manage the shared memory parallelism, so you have different thread accessing and managing the memory. There are a lot of, the main parallel code, the scientific parallel code are usually written a hybrid of MPI, OpenMP. There are a lot of other technologies you can use for talking to a GPU. There is a different type of languages. So the point is that the configuration of a system can be very complex, and you have to know very well how the system is configured and what you want to do, what is your problem, to try to perfectly, or the best you can, map your algorithm on the resources you have. And there is also, okay, this is a quick, there is also in my example an MPI code. I don't know if we have time to go through all the examples and write this MPI code, but this is actually a real MPI application that it's all there. You will have to load some modules because you need additional software and libraries to compile. You need to compile the code, so from like it's C if I'm correct. It's a C code that you need to compile to produce an executable. And you will see that the compilation is made not with a serial, it's made with MPI compiler because it's an MPI code. And basically this will generate at the end a file, an animated file with the results that you can copy back to your machine. It's, as I told you, it's a sophisticated, it's a complex example, but it does a lot of things that I explained you today, like for example, using the right partition for storing the file that produce. Like this is set into GPFS, Scratch. And yeah, and they use like srun command to run this wave executable in parallel. Again, if we have time, we can see how you submit this, how you run this, and to check quickly the output. But this is the last example in my list of examples, so only if we have time, we'll go through. And with this, I finished my presentation, and I would also like to thank a lot of my colleagues that helped me with these slides and the material. This is some of them. BSc for the computing time, and the CompBioMed, the organizer of this training for this opportunity.